thanks, Kumar, for the opportunity to spend the next hour with you. I know that a couple of you have heard earlier versions of this talk, but at the very least, we have a new doc, and she hasn't heard any of this, so it's all new to her. And if any of you has a question or comment about any of this, I'm sure it would be much more interesting than the slides I've actually prepared. And so the more interactive this all can be, the more fun I'll have. So I want to tell you a story about period maps, and specifically occult period maps. And so before we get into it, I just want to tell you the kinds of facts that we are, as a group, we're going to try to explain today algebraically or arithmetically. So suppose, to fix ideas, that you decide to think about non-hyperelliptic curves of genus 4. And you know that there is a Torelli map where you would take one of these curves and you associate to it its Jacobian, which is a principally polarized abelian fourfold in this case. And if you just see what's happening complex analytically, you'll see that there is a map where the inputs are all the complex non-hyperelliptic curves of genus 4, and the outputs are elements of the relevant period domain. So this is the Siegel upper half space modded out by automorphisms of the markings. You're basically identifying a curve with its with a set of its periods. Now, the right-hand side here isn't just a complex analytic space, it's a 10-dimensional algebraic variety. And it has a nice uniformization because I've handed it to you as a quotient of the upper half space. But this thing here then winds up sitting, this is 9-dimensional. And so inside here, it's a divisor. And so the fact that we have this beautiful uniformization of the ambient space doesn't actually tell us anything about the geometry of the moduli space of curves of genus 4. Too bad for it. But so it's surprising that somehow Kondo manages to construct an immersion of an open immersion from the set of non-hyperelliptic curves of genus 4 into an arithmetic quotient of the complex 9 ball. And this notation is a little squirrely. What I actually mean, though, is a marker for there is a Hermitian form on a z of zeta 3 lattice of signature 1,8, and gamma is basically the integer points of this automorphism group. But the part I want to focus on is that there is this surprising identification of this space with an arithmetic quotient of a 9 ball. There is another story which works like this. So if you take a complex cubic surface and you write down its Hodge diamond, then it looks like this. And the issue here is that typically when you're deforming a Hodge structure, what you're doing is you are deforming a filtration, the way that a subspace sits inside a bigger space. There's a Grassmann problem attached to that. And the study of all the 7-dimensional subspaces of a 7-dimensional vector space isn't that rich. And so the Hodge filtration is trivial, and the period map has no information. And that's why you should be surprised that on one hand, Dokachev and Prym and Kondo, and on the other hand, Alcott, Carlson, and Toledo were able to show that there is a holomorphic open inclusion from the moduli space of cubic surfaces to an arithmetic quotient of, in this case, the complex 4 ball. And so something weird has to be happening here because a cubic surface itself doesn't really have any periods. And the goal today is to try to explain where these maps come from and how we as number theorists and arithmetic geometers are allowed to think about them. So I need to back up a bit before we go forward, and if just because some of you, if nothing else, we can fix some notation here together. And if you have any comments or feedback or questions that we go through, like, bring it. So suppose you have a family of smooth, complex projective varieties, and everything inside is smooth. And then if you look at the jth cohomology of this family, you get a family of Hodge structures. And in doing so, you can extract from the situation a period map where each point, each member of this family gets sent to a point in the Grassmann whose job it is to parametrize the kind of Hodge structures that are showing up in your family. And it is certainly possible and advisable to make this more precise, but I think this is the appropriate level of resolution right now. And if I'm wrong about this, then when you want to get into the details, that's totally fine. And so the kind of, you've seen, some of you have seen many, many examples of this, and all of you have seen at least some examples of this. So if you have a family of smooth projective curves of genus G, then you get the kind of period map I was talking about on the first slide. In favorable conditions, you can actually tell what the members of this family are by looking at what the corresponding Hodge structure is. And so the kind of example of all of this is what happens with curves. So if you have a family of distinct curves of genus G, then the period map you get to this arithmetic quotient of the Siegel G space is actually an inclusion, which just says that a curve is known by its Jacobian as a polarized abelian. And sometimes cubics have good period maps, and sometimes they don't. So cubic curves over the complex numbers are just elliptic curves. And a complex curve x of genus 1 basically is a living piece of H1, right? So it's, you feel like it is the complex structure on, you take H1 and look at its real points. And so if you believe this, and you should, then it's not surprising somehow that the extent that a Hodge structure is some data showing up on what happens when you tensor the integral cohomology with C, you can see the elliptic curve living inside its H1. A non-example is for cubic surfaces. And again, the middle cohomology is rigid, and the odd cohomology is trivial, and the zero and top cohomology don't do much either. And so the Hodge theory doesn't distinguish cubic surfaces from each other. A non-trivial example, which was used to spectacular effect by Clemens and Griffiths, is if you have a family of distinct cubic threefolds, then
sorry, Jeff,
come on.
In the case of cubic surfaces, so the 1-1 probably has an algebraic part and a transcendental part, right? At 7, does it break up?
Right. So no, actually. So you can actually see everything is pick.
Everything is what?
Everything is concentrated in 1-1.
No, I understand, but I'm saying that is there an algebraic part? There is an algebraic part, but there's a transcendental part there too, isn't there?
The transcendental part is trivial.
It's trivial?
Yeah, you have all the lines on the cubic surface.
Oh, of course, this is the classical theorem, right?
Yeah.
Okay, right.
No, great. Thanks for keeping me honest. But we will see other examples in a little while where what we're going to do is we're going to be looking at some cohomology group, and we are going to know that some part of it comes from divisors or from algebraic cycles because we put them there, and then and so that kind of is interesting from a cycle point of view, but those are rigid somehow in families. But the rest of the Hodge structure is kind of rich, and that captures enough information to distinguish our objects. So you had the right answer, but it will only apply to a different collection of examples. Is that what you were asking about?
Yeah, exactly. Thanks.
Great, cool, thanks. So if you have a family of cubic threefolds, then they are distinguished by their H3s. And so the way I'm expressing it right now is that if they are all sort of pointwise distinct, then you get an embedding from the complex points of this family into this quotient of Siegel 5 space. And So far, I've only been able to express myself in terms of maps of analytic spaces, but we can do better. So if, right, this is decaf, but I'm trying to trick my brain to thinking I'm drinking coffee. So if D is any Hermitian symmetric domain, so this is a special kind of period domain which can show up, and if gamma is torsion free or neat, then this quotient space isn't just a transcendental object or an analytic object, but it's actually quasi-projective. So it's carved out by algebraic equations. And then there's this wonderful extension theorem by Borel, which says that if you have a holomorphic map where, V is supposed to be algebraic here. And then so if there's a holomorphic map between these algebraic objects, then it's actually algebraic. And this is not something you get for free when things aren't projective. So remember, there are zillions of maps from C to C, which are holomorphic but not algebraic. So something rigid happens in the presence of this situation, in the context of this situation. And then if you're willing to get slightly stacky, you can remove the torsion freeness. And so you all know that, or even I know, that the classical trailing map is actually a map of algebraic stacks or orbifolds where the inputs are the complex stack of smooth projective curves of genus G, and the output is principally polarized abelian varieties of dimension G. So we've moved things now from the transcendental world to the algebraic world. And sometimes we can even do arithmetic on objects. So if D is a Hermitian symmetric domain, and this, you can think of this if you want as a fancy version of the upper half plane, then when you form this quotient, the theory of Shimura varieties gives you a canonical model over a canonical number field attached to this thing. In the case of modular curves parameterizing elliptic curves with data, this number field is just Q. And so then the situation is, if you're given a variety over C, sorry, if you're given a variety over E, and a map from the complex variety, from the complexification of V to the Bailey-Borel model of the Shimura variety, does this actually descend to a map of varieties over E? And maybe it does, and maybe it doesn't, but it's always good when it does. And so the prototypical example, again, I keep coming back to this, is that there's actually a map from MV to AG, which makes sense over Z. And if you base change this up to the complex numbers, you get the map guaranteed by Bailey-Borel, which in turn is the algebraization of the map on points, where you take a curve and you compute its periods. In a really good situation, you can move interesting structures from here, from this arithmetic quotient of a Hermitian symmetric domain, back to the varieties you actually care about. So on the modular curve side, or on the Shimura variety side, you have CM points, which you can use to develop a reciprocity law. And you have Hecke operators, and you have modular forms. These are all things that, as number theorists, we're interested in. And if you have an open arithmetic period map, then practically all of your target Shimura variety is filled out by varieties you understand, by moduli points of varieties that you might understand, like curves. And so when you have a structure like, and actually in favorable conditions, you can also characterize the complement here. And so then you can take all this good stuff here and pull it back to V. And so then you can start, if you want to, you can ask questions like, what is the Hecke orbit of the cubic surface? So as an example, in a follow-up to the work by Alcock, Carlson, and Toledo, Alcock and Freitag computed equations for the moduli space of cubic surfaces using modular forms attached to this unitary group. And so they actually have a beautifully explicit equation where the moduli of cubic surfaces has an intersection of various cubic eightfolds in projective 9 space. So there are actual equations on this space coming from modular forms. And it turns out that in the middle of the 19th century, a lot of really beautiful work, energy was put into cubic surfaces, and a lot of beautiful work came out of it. And part of this was Cayley had a kind of generalized cross ratios he was using, kind of inspired by our understanding of the moduli elliptic curve as the lambda line up to cross ratios. He had a system of cross ratios for understanding cubic surfaces. And after the fact, we can recognize what he was doing as computing modular forms.
So Jeff, is it supposed to be obvious that, so this is writing cubic surfaces as a complete intersection, is that right?
The moduli space of cubic surfaces, yes.
Yeah, right.
Yeah.
Is that even obvious? I don't think it is, no?
Certainly not to me. It might have been to the ancients. I'm not totally sure. But before you do anything, there's no reason to hope that this will be true.
Sorry?
But if you stand at it from afar, if you don't compute anything, I don't think there's a way to know that this is going to be true until you compute something and see that it is. Yeah.
Interesting.
Sorry, just wondering how many cubic eightfolds do you need to cut out this moduli space?
I think it's a complete intersection, and
wow,
I know that the target moduli space is dimension 4. So up to that, then we know, but I'm not 100% on this.
That seems kind of strange to me because I mean 5 cubics in P9 is highly general type, whereas the moduli space of cubic surfaces certainly isn't. But I guess if it's singular enough, it could be.
That's I'm going to write this down because I don't know the answer. Okay.
Okay, thanks.
Yeah. So. The situation isn't going to improve in the next 40 minutes, but this will give me something to look up. So thanks, Adam. Sorry. Other questions I can gather or defer or maybe even answer. Okay. All right. So I'd like to explain the cubic surfaces situation, but I'm not in a position to quite yet. So I want to go up a dimension to cubic threefolds where things are less 19th century, but kind of easier to access with late 20th century techniques. So suppose you have a cubic threefold. Then the Hodge numbers of the middle cohomology are 0, 5, 5, 0, which means that so at least there's a chance that when you deform a cubic threefold, you are deforming a 5-dimensional subspace of a 10-dimensional space. And so there's at least a chance that there is some interesting geometry being captured by this Hodge structure. And then an accident happens, and well, I can explain the accident in a minute, but so you are always encouraged to form in odd dimensions the intermediate Jacobian attached to a Hodge structure. And so the way you do it is you mod out by half the Hodge structure, and then you mod out by the integral periods. And when you get, if X is just any old smooth projective variety or smooth Kähler, compact Kähler variety, you'll get at least a complex analytic torus. But in this case, because the Hodge structure is of level 1, it's concentrated in the middle. It doesn't have anything on the side somehow. The complex analytic torus is actually an abelian variety. And the cup product, which pairs H3 with itself into H6, then gives a principal polarization on this. And so given X, we can now construct a principally polarized abelian fivefold. And the Clemens-Griffiths Trelli map, or Trelli theorem, says that you get this period map, which is an inclusion from the moduli space of cubic threefolds to the moduli space of principally polarized abelian fivefolds over C. And one fact I'd like to tell you about is that, so The moduli space of cubic threefolds makes sense over any ring at all, although it's slightly scarier working within characteristic frame. And the moduli space of principally a polarized abelian fivefolds is also an object that makes sense over Z. And so what I want to prove to you now in a couple of different ways is that this map, which was constructed or defined purely transcendentally, actually descends to Q. And I know of at least 3 different proofs of this, and each of them tells us something slightly different about the world. So the first proof goes back to a monodromy calculation of Deligne in the early 70s. And my impression is that what was happening is that Deligne was about to prove the Bay conjectures for basically everything, but he couldn't quite yet. So he had these kind of smaller but still beautiful papers, right, where he proves the Bay conjecture, where he analyzes the cohomology of K3 surfaces, for instance. Another thing he did is he was looking at other families of varieties where he knew how to canonically attach an abelian variety to another kind of variety and use that to move information around. And so his argument roughly is as follows. He considers and he does this for all known families of Hodge level 1. But in the space of, in the case of cubic threefolds, which already has all the ideas, it goes like this. You start with a universal family of cubic threefolds, and following Clemens-Griffiths, you construct the family of intermediate Jacobians over the same space. And because of the way you've constructed it, H1 of the tape model of this relative Jacobian is the same as the middle cohomology of this family of cubic threefolds. And he says, look, I'm Deligne, I know how to compute monodromy, and this thing, since it's a general family of cubic threefolds, has a really big monodromy group, which means that the automorphism group of the associated abelian variety is trivial. And so I know that forms of an abelian variety over something big are classified essentially by cocycles of the fundamental group with values in the automorphism group. So when the automorphism group is trivial, the whole mess has to descend to Q. And he conjectures that this should work over Z, but he can't get there. Or he doesn't feel like getting there, probably more accurate. Here is a second approach to this thing. So here, Beauville and Miller had worked out how to make the intermediate Jacobian an algebraic construction. And the game is played like this. You start with a cubic threefold, and after blowing up a line, you can fiber this over P2. And the residual over a typical point, so you always have, since this is a cubic, the fibers are degree 3 things, and they always have this line that you're projecting from. So the fiber is a line and a degree 2 thing. And typically that degree 2 thing is a smooth quadric, but occasionally it's not. There is a discriminant curve in here which parametrizes, which corresponds to those points where the fiber is a degenerate quadric instead of a nice quadric. And then the pair of lines that this quadric degenerates into gives a canonical 2-to-1 étale cover up here. You can view this double cover as living inside the Fano variety, whose job it is to parametrize lines inside this cubic threefold. And so from X, we eventually extracted an étale double cover of curves. And so there is a principal polarization, not just on the Jacobian of delta tilde, but on the complement of the Jacobian of delta inside delta tilde. That's this kind of nice numerical or geometric accident. And so we can extract from this a principally polarized abelian fivefold when the dust settles. And if we play this game over C, we recover the Clemens-Griffiths intermediate Jacobian. And if we play this game over a fairly arbitrary base, then we can get this over any family we like. including the universal family over Q. This is a little too fast to absorb all details of, but what I want to do with this and even some more elaborate constructions we'll be talking about in a bit is just give you a feel for what kinds of geometry are involved. So this is an argument which makes sense in families, and so it makes sense arithmetically.
Jeff, this is your result, right?
Yeah, sorry. Yeah. This kind of looks awful. But so I've been having a lot of fun with Jano Castellana Martin in Boulder and Charles Vial in Bielefeld for the past few years, thinking about what other parts of transcendental geometry we can capture and bring back to algebraic geometry and even to arithmetic geometry. And one of the things we were able to do is say, so if you have a variety over Q, say Q right now is my subfield of C, but it doesn't really matter, then you can go up to C and construct its intermediate Jacobian. And that's typically a complex analytic torus. And as arithmetic geometry, we don't have a lot to say about it. But inside there is a biggest abelian variety, and its job is conjecturally to classify, to receive receive the Abel-Jacobi invariance of algebraically trivial cycles of the right dimension. So there is an abelian variety inside the intermediate Jacobian, which knows about algebraically trivial cycles on this variety. And that at least is an abelian variety. And so then the question you might ask, and we did, is does this complex abelian variety remember that it's attached to something which started off life over Q? And the answer is yes, that this algebraic intermediate Jacobian does have a canonical model over Q, or over the base field. And what makes this the best model, or the distinguished model, is that, so there's an Abel-Jacobi map where the inputs are algebraically trivial cycles on X of codimension n+1, and the outputs are elements of the intermediate algebraic Jacobian. And so if X is defined over Q, then this thing has an action by the automorphism group of C over Q. And if we put a Q structure on this complex abelian variety, then we've put an aught C over Q structure on its complex points. And so what makes this model the best model, or the natural model, is that this is the model which makes this Abel-Jacobi map aught equivariant. Questions? It's too late to say less, but I could say more if pressed. Anyways, armed with this, you can then give a very fast proof that these kind of period maps for level 1 Hodge structures descend to a field of definition. So if you have any family of smooth projective varieties of dimension 2n+1, and if you assume that all the varieties have their Hodge structure concentrated in the middle, and this is just a slight generalization of cubic threefolds, then the induced map from T to AG as complex varieties descends to Q. And the proof is just that thanks to all of this nonsense, if you construct the graph of tau, this complex Torelli map, it's stable under the automorphism group. So poof, it descends to Q. You can actually get algebraicity out of it this way too. All right, but I was supposed to tell you about the unusual period maps, not just the classical ones. So I want to go back to the kind of opening statement here that there's an open immersion from the moduli of cubic surfaces to an arithmetic quotient of a complex four-ball. Remember, you're supposed to be surprised by this because the Hodge structure of a cubic surface is rigid. And so Kudla and Rappaport call this map an occult period map because what you're doing, it turned out, is you're not measuring the periods of the cubic surface, but of some other object attached to the cubic surface. And so it is a hidden period map, which doesn't lie on the surface, but you have to explore a bit to find it. And then you might ask, is there a possibility of descending this map? So this thing makes sense over, over Z, although it's kind of scary and characteristic-free. And this thing admits a canonical model over Q of zeta 3, thanks to the theory of Shimura varieties, and even over Z of zeta 3. And so you could ask, is this period map compatible with these structures? Actually, I can be a little less mysterious about why this has a canonical model. It turns out that for this particular set of data, this ball quotient is the complex points of the moduli space of abelian varieties with an action by Z of zeta 3 of signature 1, 4. And so once you've made this identification, then when I state the arithmetic version of this, what I mean is this, just over Z of zeta 3. And Kudla and Rappaport were able to show that the occult period map descends to Q of zeta 3. And they do this with a kind of Deligne style monodromy calculation on the Hodge structures that show up over here by pulling back what's happening here. That there's so much scrambling around that there are no automorphisms, so the whole mess has to descend. So here's how Alcott, Carlson, and Toledo do it. If they start with a complex cubic surface, and they construct a map, cyclic triple cover of P3, which is ramified along Y. So if Y had an equation f of x is 0, then this has an equation like z cubed equals f of x. And so then what their period map does is it measures the periods of Z. So there's a map from the complex points here, whoops, sorry, not to Z of C, that should be to, sorry, not to one thing, but to the whole mess of all of them. Sorry about that. The laser pen, go. Good. So from a cubic surface, they extract a cubic threefold, and they know how to make an intermediate Jacobian out of that. So that winds up, so they get a principally polarized abelian fivefold. But it's not just any old principally polarized abelian fivefold. The fact that Z was constructed as a mu3 cover means that there is an action of Z of zeta 3 on the Jacobian they construct. And you can do a calculation, or they can do a calculation, and find that the signature is 1, 4. And so this map from cube 2 to cube 3 to A5 factors through this thing. And then there's a dimensional accident where this and this have the same dimension. And that's the source somehow of their period map. Sorry, maybe source is the wrong one. That's the construction of their period map. And so you can show that their map constructed in this way is compatible with all these other maps that descends arithmetically. So the proposition is that there is a diagram of stacks, and I got kind of like maybe halfway to getting it over Z of zeta 3. So I had to invert 2 and 3. So there is a map from, so the thing that we're trying to analyze is this. And there is a stacking mistake I made in a published version, so I'm trying to set the record straight right now. So if you have the stack of triple covers of P3 branched along a cubic surface, there's a map from this to cubic threefolds. And then from this to A5, that's the intermediate Jacobian map. And from here, you can also get a, and this map factors through the moduli space of principally polarized abelian fivefolds with an action by Z of zeta 3 of signature 1, 4. if you look at the ramification locus of this thing, you'll get a cubic surface out. And this is an open immersion. This is at least an isomorphism on coarse moduli spaces. And so you have an open immersion of coarse moduli spaces between the moduli space of cubic surfaces and this Shimura variety. And that's the best statement I know in this direction. So Kondo can stare at just about any situation and see the K3 in it in a way that he is very good at, and I am really horrible at. I had never worked with K3 surfaces before, trying to work through a little bit of the Dolgozhov and Kondo corpus. But here's how they play the game. And again, this is a little bit too fast, but it should give you a flavor for what's happening. They start with a cubic surface. They choose a line, and this is much like where I had blown up. They're just looking at the set of planes through a line. But for a generic hyperplane through their favorite line, you get a smooth quadric, but sometimes they don't. And so the locus of parameterizing hyperplanes where they don't get a smooth quadric, it turned out to be a singular plane curve of degree 5. And they define a double cover of degree 6. And then they look at the double cover of P2 ramified along this thing, which in turn was, if you remember, a certain sextic cover of the discriminant locus. And now they have a polarized K3 surface, and it has a mu3 action. And what they compute is the periods of Z, by which I mean the transcendental part of the cohomology of this K3 surface. And that's the source, and that's how they construct their period map. And so there's room to hope that maybe you can do something similar in an arithmetic context. And so to explain this, I need to take a slight detour into the world of K3 surfaces. But just to emphasize what I said before, so at this point, I want to at least make sure I've explained the title. So you're given a variety Y, and you try to understand it by constructing a new variety Z, like so for ACT, it was a cyclic triple threefold. For Dolgozhov, Prym, and Kondo, it's an exotically constructed K3 surface. Compute the periods of Z and hope that tells you something about Y. And so Kudla and Rappaport went through a list of known constructions, and the target of the period map is the Shimura variety. And so they show that the occult period map descends to the natural reflex field that shows up. All right. So I want to tell you a little bit about moduli K3 surfaces and Shimura varieties to be able to get to some of the applications of all this. So if you fix some D, you can look, and probably should look, at the moduli space of K3 surfaces with a primitive polarization of degree 2D. And so you hand it S, it hands you back all the set of K3 spaces over S, where you have chosen some section of the Picard bundle, which is primitive and pairs to degree 2D. So this is like a fancy version of the moduli space of quartic surfaces. One way of interpreting this is that when you chose lambda, or when you let me choose lambda, you chose a primitive embedding from a lattice Z where the generator pairs to 2D into the lattice, into the Picard lattice of this K3 space. And once you look at things this way, then you're free to make a generalization of lattice polarization. So you fix your favorite lattice inside the kind of Ur lattice, which controls K3 surfaces, and ask it to be primitive of signature 1R-1. And you can construct the moduli space of L polarized K3 surfaces, where what this alpha means is you shove into the Picard group your favorite lattice. And so this is a kind of natural generalization of the moduli space of K3 surfaces. To the best of my knowledge, it was introduced formally by Dolgozhov in a paper in the mid-90s, but it wouldn't surprise me if there were antecedents for this much earlier. Into every module I talk, a little group action must follow. So this is kind of a notational heavy thing, but it's to get us where we need to be to express the things we need to express. So you can look at the moduli space of lattice polarized K3 surfaces with an action by mu n. And then you could pick out, if you want, your favorite kind of action by mu n. So the job of this character is to tell you how does mu n act on the cohomology of your variety. And we're going to insist that mu n act faithfully actually by a certain character on the one-dimensional space of two forms, and that it acts trivially on the lattice and nothing bigger. So all that's reasonable to get from this is that you could, if you wanted to, define the notion of L-polarized K3 surfaces with your favorite kind of action by a small group of roots of unity. And if you do this, and if you stay away from the discriminant of the lattice and the size of the group of roots of unity, you can get a smooth Deligne-Mumford stack over zeta n. And this is a slight generalization of something Dolgert had done over C. I've been kind of chatty today, so I'm going to start moving quickly through this. So anybody who is bothered by this is welcome to look at the slides or talk to me later. But the point is that if you choose a marking of a complex K3 surface to some identification of H2 with this lattice, then from this situation, you can extract a period point. So this is how does H20 sit inside the total H2. And you can do this so you get a period map then from K3 surfaces to the period domain classifying these things, modded out by automorphism. And the only problem is this is a really horrible space. So instead, you just work with the primitive cohomology, the part which is relative, which is orthogonal to the polarization class. And so you wind up inside a, you wind up with a smaller period domain inside the period domain associated to the total K3 lattice. And so there's a period map from the moduli space of degree 2D or D polarized K3 surfaces into this quotient of a Hermitian symmetric domain by an orthogonal group. And that's actually reasonable. In fact, it's beautiful. So there is an open immersion from the moduli space of polarized K3 surfaces into an orthogonal Shimura family. If you redo this whole thing and replace 2D with your favorite lattice, as long as you're not too crazy about the lattices you favor, you will get a similar story for lattice polarized K3 surfaces. So that's the moduli of K3 surfaces. On the other hand, we have the moduli space of, say, abelian varieties with some extra data. So if you start off with a Hermitian symmetric domain attached to some reductive group, then you can start forming generalized versions of modular curves, which algebraize to complex quasi-projective varieties. And then it's been known for a long time that these things descend to a reflex field, a canonical number field, which emerges from the data used to specify your moduli problem. And if you promise to stay away from level P structure, then you can get a canonical integral model over the ring of integers of this this field if you invert a handful of times. And a couple of salient Shimura varieties which show up in this study are things attached to a lattice of signature 2n. And this will wind up being not the lattice we care about, but its orthogonal complement inside the moduli space of lattice polarized K3 surfaces. And unitary Shimura varieties attached to quadratic imaginary fields, say. Where you specify some data, and then you find that the Hermitian symmetric domain associated to it is some complex unit ball, and you can form the Shimura variety. And in all the cases that are going to show up here, you wind up with the moduli space of abelian varieties of the right dimension, equipped with an action by the ring of integers here of the specified signature, and maybe with the principal polarization, or maybe with something a little bit different. All right. So with all the definition, which notation, which I blitzed through in the past 5 minutes, then the Dolgotov period map becomes a map from the moduli space of lattice polarized K3 surfaces to the complex points of a Shimura variety that one can attach to this data. And you can do something similar where you add in an action by some roots of unity. And it looks a little different depending on whether you're just adding on a +-1 action or some honest like zeta 3 or zeta 5 action. And the period map in this case gives you from lattice polarized K3 surfaces with your favorite action by UN to an associated Shimura, the complex points of an associated Shimura variety. In the past 20, 15 years, it's become clear that the Koteski-Shapiro or Shafarevich period map actually descends to a morphism not just over Q, but then even over Z, practically, where you stay away from 2 and 3 and Z. So this transcendentally defined map preserves the natural integral structures on this side and on this side. It's not even clear it preserves the Q structure before you start, let alone the integral structure. There's a lot of gorgeous, serious math that went into these works. And from this, you can bootstrap and get the analogous situation statement for lattice polarized K3 surfaces. So specifically, the map from RL chi to the associated Shimura variety descends to the ring of integers after you invert n and the discriminant. And the proof of this is you bootstrap from what smart people have done by looking hard. Let me get to some of the applications real fast. So if we go back to Kondo's result, this is how we can now interpret it with the kind of technical garbage from the past 10 minutes. So here, roughly, is what Kondo does. He starts with a non-hyperelliptic curve. Its canonical model is the intersection of a quadric and a cubic inside Q3. So he constructs the triple cover of this quadric, which is branched along C. And so now Q is a quadric, so it has 2 rulings. And so you could let M1 and M2 represent the classes of these 2 rulings. And if you let Ni be the inverse image up here of representatives for each of these rulings, you'll get cycles, or at least cycle classes on Z. And each of these things turned out to be an elliptic curve. And if you take the intersection product of one with the other, the number you'll get is 3, not something else. So then Z is a K3 surface. And the fact that you carefully put in N1 and N2 means that you know about something non-trivial happening inside the Néron-Severi group. And so you can map a hyperbolic lattice scaled by 3 into the Picard group of Z. And Z also has a mu3 action because of the cyclic triple cover thing, which fixes each of these n sub I because these were the inverse images of ramification. And so from C, Kondo was able to extract the data of a K3 surface polarized by this lattice with a good action by mu3. And so then with this setup, you can show that there is a diagram of stacks of integral stacks where you can map from this moduli space of K3 surfaces to the associated Shimura variety. And this is the take the quotient to recover the curve. And this is an isomorphism on coarse moduli spaces. And if you are less profligate with your time in the beginning of the talk, you can do this kind of construction for other examples. But so the other flavors of curve, the 5 points on a line. I want to get to an actual kind of application because this is heavy stuff to move on. 6 points on the line. All right. I now want to show you the world's worst way to compute the 27 lines on a cubic surface. That seems like a reasonable place to stop and remember to move somewhere. So it's been known for like 150, almost 200 years that a cubic surface over an algebraically closed field has exactly 27 lines. And we can now make arithmetic sense of this. So the Cayley and Salmon correspondence, by which I mean the letters they wrote to each other, showed in 1849 that a cubic surface has exactly 27 lines. And Camille Jordan got fascinated by this, and he computed the automorphism group of the 27 lines. And what this phrase means is the 27 lines, they intersect in various ways on the cubic surface. And so what you're looking for here is the automorphism group of the full configuration of the 27 lines. So it has to preserve their intersection thing. And you get what, in modern language, we would interpret as the Weyl group of the exceptional group E6. And Jordan actually interprets this as in his 1870 book, as the Galois group of the 27 lines on a general complex cubic surface. That somehow he has in mind the general cubic surface, maybe over some parametrized family. And if you work in a system of indeterminates to parameterize your cubic surface, then you can look at the automorphisms of the equations you get by trying to write down the 27 lines, and that's what you get. So with a little bit of anachronism, if you let, okay, a lot, put an M up here to say it's the data of a cubic surface and a marking of the 27 lines, an identification of it with this abstract configuration. Then there's a forgetful map from the moduli space of marked surfaces to the moduli space of unmarked surfaces. And if you want to, you can interpret Jordan's theorem as saying that this space is irreducible, and it is Galois, and the group is the full automorphism group of the configuration. And then something kind of amazing happens, which is that if you trace through what the oval-Jacobi map is doing on the cubic threefold occultly associated to a cubic surface, you find the oval-Jacobi map identifies differences of lines on Z on the cubic surface with 1 minus zeta torsion on the intermediate Jacobian. And so there is a map then where the moduli space of marked cubic surfaces is open in the moduli space of abelian varieties with an action by zeta 3 of signature 1, 4, and an identification of the 1 minus zeta torsion. And the forgetful map here is followed by the forgetful map is parallel to the forgetful map here. And so as a consequence, if K is Hilbertian and Z is general, then the Galois group of the 27 lines is the Weyl group. And the proof is that, well, the generic fiber of this map is irreducible. Or sorry, the complex fiber is irreducible. And so this is irreducible. But we have a theory of toroidal compactification for moduli spaces like this. And so each of these things has to be connected using Zariski connectedness theorem. And then we have Hilbert irreducibility, which says that this then this irreducibility propagates then for a fairly general point with values in the Hilbert field. Another modest payoff is that if you have a large finite field, then the expected number of lines on a random cubic surface over FQ is about 1. And the point is that if this has geometrically irreducible fibers, then so does the data of a cubic surface and a line. Then this has about the same number of points over FQ as this does. If you average, if you divide one by the other, you get about 1. So now there's this way of getting information back and forth between Shimura varieties and, say, moduli space cubic surfaces. And I've just pushed things in one direction, but it seems plausible that for those of you who are really good at counting objects over finite fields, you can tell the Shimura varieties people something new. Thanks for your time. I realize I pushed the boundaries of the time a little bit, so skitter off if you have to, but if you want to ask questions, I'm around. Thanks a lot.
Okay, first let's thank Jeff for a really interesting talk. That was a lot.
Sorry, I got
no, but it was beautiful, and I think it's clearly something I'd like to reflect on a little bit more detail. Do we have any questions, quick questions for Jeff? You can either, they're not, we're a small group, so you can just speak out if you have a question, or you can raise your hand if you like.
Again, I'm sorry I tried to cram too much, and I just got excited when I was thinking about this stuff.
Well, you got us excited too. So.
Yeah. Yeah, I'd like to ask a couple of questions if I could,
Adam,
actually.
Yeah, go ahead.
Yeah, Adam, please, that'd be great.
So first of all, I'm wondering, so you had this rather nice construction that you described of going from K3 surface, going from a cubic surface to a K3 surface.
Yep.
So I'm just wondering, could you, instead of doing that, could you just, fix a hyperplane in P3 and think of the log K3 surface given by the cubic surface with that hyperplane section removed?
Why? So tell me more about what a log K3 surface looks like. So the answer is quite possibly, and now we are way out past stuff I know. So could you tell me a little more, Adam?
Well, okay. So I guess in general, a log K3 surface is, well, I guess you could say really, concretely, it is a Fano surface together with an anti-canonical divisor. And right, so I don't really know anything about the period maps associated to such things, but I think that there are some. In many ways, sort of the general philosophy, right, is that if you have any property of variety that is determined by its canonical divisor, then that is of complete varieties that are determined by the canonical divisors. That's sort of a pale shadow of some property of an open variety, for which the analog of the canonical divisor is the boundary divisor that you deleted plus the canonical.
Okay.
So I'm wondering to what extent you can make similar constructions in this context. Unfortunately, I don't really know anything about them.
What's interesting about this is that it sounds like you are unsure about some aspects of this, and I am completely ignorant of others. So I think there is maybe sometime we can talk about this later. So we can see if we can work something out together, because I don't know this part of the story at all, and I'd really like an excuse to learn.
Thanks.
It'd be much more fun doing it with somebody else.
Yeah, perhaps you should. So another question I was wondering about. So I mean, we've been talking. I unfortunately missed your first two slides. You may have said something about this then, but you were talking about curves of genus 4 and thinking of them as being on well, they're the intersection, of course, of a cubic and a quadric in P3.
Yep.
Now, in the moduli space of curves of genus 4, there is this very nice divisor of curves that lie on a singular quadric.
Right.
And these, of course, are closely connected to Delpez's surfaces of degree 1.
So, yeah. So I think, what do I think? I think there's a good chance that what happens is that if you, so I am guessing here, I'm not asserting with any kind of confidence, but I think if you were to look at what happened at the boundary by introducing singular models there is, so the period map is actually open in a, you were the target is a 9-dimensional ball quotient, and you miss something, and the thing you miss is an 8-dimensional ball quotient. And so my guess is that if you put in those things at the boundary, what you'll find then is a ball quotient parameterization of moduli for these ones with a strictly singular model. And that probably descends again to the integers of a small number field. That would be worth working out. Did
Okay,
I?
thanks. Yeah,
Sorry, maybe I interrupted you before you could actually ask your question.